Hey, hello, thermodynamics students.
Hello.
I wonder who we got out there in this class. Let's see here. Oh, we got a good crowd. Brian, Nicholas, Bryce, Dawson, Reagan, Nathan, Daniel, Alex, Tyler. We got a great class, looks like here. Yeah, there's Bryce right there. Yeah. Hey, howdy, howdy. Okay, well, what are we going to do today is the question. Let me think about this. What did we learn last time? Anything? Hey, I remember we had some definitions last time. Hey, there's another student. There's Nathan. Howdy,
Hi
howdy.
there.
Good to have you.
Good to be here.
Yeah, we had some definitions of what a property is and what a state is and processes and man, I don't remember. We covered a lot of definitions. What are we supposed to do today? I think I talked about models. Yeah. Some of the models are the tables in the back of your book and the ideal gas model, the compressibility model. We might be able to mention those today. That'd be fun. Did you have any comments or questions before we tackle the big topic today is something called interpolation. That's the big topic for the day. But did any of you have any comments that you wanted to make or questions?
Hello, Professor.
Yeah. Hi.
Can you go over how you want us to set up the homework?
Yeah, there should be a link, and some of you guys have a hang on just a second. Oh, hi. I just going to tell you I've started my thermo class. Yeah. You might tune in if you have time. Everything's okay, I think, so far. Thanks. Bye-bye. Some of you have what is called a CAM scanner. It's a one of the students was explaining it to me. It's an app they have on their phone called a CAM scanner. Any of you know what I'm talking about? Yeah, Nathan does. Nathan, just explain what a CAM scanner is for the rest of the students.
Well, I hadn't heard it called that exactly, but you're right. It's just an app. You just take a picture and it converts it to a PDF scan, and then you can email it to yourself. Is what I usually do, and then you can select it in your files and upload it to the link that you provide. So
Fantastic. Well, if that made sense to you, you're a better man than I am. I'm not really a computer guy, but my daughter is. She helps me with this stuff. But I do know my thermodynamics, and between us, we'll get through this all right. But maybe that's helpful. Now, was it Bryce that asked the question on that? Who was it that wanted to?
It wasn't me.
It
No.
was somebody asked about how do we turn in homework.
No, it was me, Professor. I'm Nicholas. I just wanted to know how you wanted us to set up the page.
Oh, okay. Get the syllabus. It's Nathan I'm talking to, right? No.
Nicholas.
Nicholas, I'm sorry.
Nicholas.
Yeah, Nicholas. Get the syllabus, and it says to get some engineering paper, or some cheap graph paper will do. It has lines on it, like a grid, and you can put angles in there and draw your you can draw your items that we're talking about, your device sketches like turbines or pipelines or whatever it is on there, and label them, and then solve them using the equations that we're going to learn about. And then one of our students was telling you about that app. You can send it on that link on your homework. Now your homework, there is some homework, and according to my course schedule, which you should have, it's it's actually two problems. It's 183E. E stands for English. I think that's page 6, P6. And then the interpolation exercise, which you have to go and download that. Has anybody downloaded that interpolation exercise that I'm talking about?
Yes, I did.
Yeah. Well, that's the topic. I want to show you guys how to do interpolation today, and you're going to just answer those questions there about interpolating. See, we're talking about using the tables. We have these different models. The very best model is the tables. There's all these tables in the back of the book. Here, let me show you what I mean. Well, of course, you might have a digital book, but look, tables, tables, page after page after page of tables. Look, more tables, tables. You get the picture. Now these numbers in here are experimental. They're compared with experimental numbers by they've actually done experiments with different gases like ammonia, for an example, or steam. And they've measured the pressure and the temperature and the volume and the energy and so forth. That's the best model. Then there's the ideal gas model. It's nowhere near as good as the tables. And there's another model called compressibility. We'll show you all three of these in here in a minute. And there are even other kinds of models. I mentioned some Tuesday. Yeah. But let's learn how to work the tables first. So these are the different kind of models we have. This is the very best. Here, I'll put a happy face on that. Ideal gas model, not so happy. Not so happy. Even though ideal, it sort of sounds like ideal, like the ideal marriage. Well, in real life, you have to work at it. It's not always roses. You have to work at it. And compressibility, it's sort of in between. You'll discover it's not as good as the tables. And there are other, like there's a computer. You can get a computer program that will give you everything in the tables, okay? But what you're going to use is the tables on your ebook, electronic book. Okay, before we start with a problem, any other comments or questions? All right. Now, what I'm going to do is I'm going to look up some stuff in my STEAM table, and these are directly taken from the steam table. Now, this is just an example so that you guys can get the hang of this. But just let me show you where those are, that you could look them up. Back in here is a steam table. And I'm going to see if I can find that. Let's see. Yeah, here it is. It's Appendix A36 in the back of my book, or on your electronic book. I bet you can find it, but at 5,000 kilopascals and 500 degrees Celsius, this is the specific volume in cubic meters per kilogram of H2O. It's steam. It's hot. I mean, 500 degrees Celsius is kind of hot-ish. Okay, and at 5,000 kilopascals and 550 Celsius, and back here in the tables, it's 0.07368 cubic meters per kilogram. Remember what specific volume is. Specific volume is volume divided by your mass. And so it's cubic meters per kilogram. Volume is in cubic meters, mass is in kilograms. They call this specific volume. See, this V stands for volume, and that little m stands for mass. And if you take your volume and you divide by your mass, you get the specific volume. Now it's 6,000 kilopascals. I'm on that appendix. It's actually table B.1.3. It's table B.1.3. And at 6,000 kilopascals at 500 C, it's 0.05665 cubic meters per kilogram. And at 550 Celsius, 0.06101. I copied those down right. Are you able to take notes and pull those tables up at the same time? Is there anybody out there that's developed that skill of pulling those up to where you can verify that I got those numbers right? Anybody?
I haven't tried it yet, but I could try real quick.
Yeah, go ahead and try. Yeah, see if you can.
It's gonna take a while to load up.
Yeah, it's kind of tricky. Well, while you're trying that, maybe some others are trying it. Let's show you how to use the tables. And let's just suppose that suppose you wanted to look up suppose you had water and you knew that you had 5,000 kilopascals and 500 C. Well, then you could look it up and you know what the V is. It's 0.06857. That was easy. But what do you do? What do you do if it's in between? What if you have a problem where you got 5,000 kilopascals, but you have, say, I don't know, we'll make something up, 525 degrees Celsius. See, that's not in the tables. See, 525 Celsius, that's not in the tables. You're not going to get this answer anymore. You understand? Yeah, I tell you what, it'll be an answer in between here. You have to interpolate. Now, in this case, it's pretty easy to do because this is 1/4 of the way. 500 to 25 is 1/4 of the way from 500 to 550, isn't it? No, I'm wrong. It's half of the way, isn't it? 525 is half of the way between 500 and 550. Hey, I can do that. You just go halfway between here and you got your answer. So let me do that. Do you guys know how to get halfway between two numbers? You add them up and divide by 2, right? Okay, I'm going to do that. Here goes. I hope somebody checks me on this so I don't goof up. But I'm getting 0.071125. And I need somebody to verify that. Is that what you got? I added these two numbers and took half of it because, see, I'm halfway between these two numbers. They call this.
I guess I'm wrong. I was thinking you subtracted the difference and then divided that and then added it.
Well, you know,
I was making an extra step. I
think you could do it that way. I think you could do it that way. You should get that answer, though.
That answer is correct.
Yay, we did good. Well, that was pretty easy. Let's try one a little harder. Suppose you had something goofy like this. Suppose you had 5,000 kilopascals and 518 degrees Celsius. Well, then what's the specific volume then? Well, you have to interpolate. Now, the way you do it is you find out the, I guess, percentage of going between those numbers. See, the other one was 50%, but this isn't 50%. You know what it is? It's 18/50ths, isn't it? From 500 to 518 is 18, and from 500 to 550 is 50. What is 18/50? You know, I can do that in my head. That's 36%, isn't it? You can try it. It's 36%. So what we want to do, this answer is going to be different now. We want to take 36% of the distance between these numbers. We want to take 36% and add it on. Okay, I can do that. Here, let me write it out for you. They call this interpolation. It's really not hard. I'm going to take 36% of this difference and then I'm going to add it on to that first number. You still have to add it on to that first number. Okay, let me do that. Let's see what I get. Here goes. Well, unless I've screwed this up, I'm getting an answer of 0.0704 rounded off to 1. And I'll wait until I hear 2 or 3 students tell me they got that.
Is this
That's
for
nice.
518 degrees?
Yes,
I got the
500. Good. 518 degrees. If you have water at 5,000 kilopascals and it's at 518 degrees Celsius, then the specific volume is 0.07041 cubic meters per kilogram. We're doing okay, aren't we? Well, let's do another one. Okay, that was pretty easy. And here, let's try another one. Do I need to wait a minute? Maybe there's some people trying to catch up.
How did we get to 36%?
Oh, thanks for asking. If you go from 500 to 518, that's a difference of 18. To go from 500 to 550, that's a difference of 50. Put that in your calculator and see if it doesn't come out to be 0.36.
And why are we doing the difference between 500 and that number? Is it the closest one next to it?
Well, we want to find the number that goes with the 518.
Oh, I see now, because I see why we're using 500. Thank you.
Oh, okay. Good going. And maybe we should do another one if you're happy with that. Let's do another one. Here goes. Okay, I'm going to erase all this. We'll do a totally different one this time. All right, let's suppose you had, let's suppose this time you had 6,000 kilopascals. You're working a problem, and you know it's water vapor. It's steam, actually. 6,000 kilopascals. And suppose the temperature is, I'll make something up. Suppose it's 541 degrees Celsius. We want to know what the specific volume is. Do you understand that it's going to be between this number and that number? It's because 541 is in between 500 and 550. So it's going to be in between here. Which will it be closer to? Will the answer be closer to this first number or the second number? What do you think?
The second one.
Yeah, because see, 541 is closer to 550 than it is 500. So whatever this answer is, it's going to be closer to that. Well, here, I'll shut up and see. I'll see if you can do it, and then I'll do it and write the equation for you. See if you can find out the V that goes right in here between these two numbers. Go ahead. Well, I got my answer. I'll tell you what I got. I haven't double checked it. It might be wrong, but here's what I got. I got 06 0225.
That's what I got.
Yay, I'm glad to hear that. Here, let me write it out for you. See, if you go 541, then what you have is 41/50 of the way from here to here. And you have to multiply by this difference, which is but then you're not through yet. You have to add the beginning value. And what I got was the 060225. See if that isn't what you get. We'll take a minute for you to double check that. And then we'll move on. Anybody else getting that?
Yes.
Yay, good.
Yes.
Yes, sir.
Yay, good deal. Okay, well, let's do one more of these, and then we'll do something different. I'm going to erase all that now. You guys are taking excellent notes. I know you're writing that down in your notes, making sure you understand it. You better write it down because I'm going to erase it. Here goes. It's going to go bye-bye. Here goes. Here, let me get rid of that 541. And that was the answer there. Okay, let's erase this and do another one now. Okay. Now this time we're going to go backwards. This time I'm going to give you water. I'm going to give you 5,000 kilopascals. But I'm going to give you the specific volume. Suppose the specific volume is 0.070, a bunch of zeros. Hey, this time we know this. See, and it's in between those two, and we're trying to find this. And what you have to do is you have to find the fraction or the percentage from here to here versus from here to here. Now I'm going to do that. Here, I'll write it out for you. This is called back interpolation. And we're going to have to do that too. First, we're going to do that. All that's going to do is give us that percentage of how far we want to go from here to here. So I'm going to do that now. Here goes. Well, if I did that right, this comes out to be 0.2798. What was that? 28%. We want to go 28% of the way from here to here. So what you do is you multiply that percentage, 2798, by this difference, which is 50. And then you add it to the 500. And that'll give you your new temperature. Okay, I'm going to do that now. I'm just going to round this off. I'm getting 514 degrees Celsius. This is called back interpolation. We went backwards. Did that make a lick of sense to anybody?
Mr. Griffin, can you do it again? Because I didn't understand that, how you get the 514 temperature.
Explain how I got the 514. Yeah, sure, be glad to.
Because I think the camera is a little bit up, so I can't see what the numbers are at the bottom.
Oh, okay. Well, here, let me write it where you can see it better. Now, is that my friend Mohammed that just asked me that?
Yes, Mohammed.
Yeah, Mohammed, you understand the problem now. We're trying to find this 514. We don't know what it is, but we do know this is 07. So what you got to do is you got to take the 0.07, subtract the 0.06857, and divide by the big difference between the first and the last, 0.7368 minus la, 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 la. I think you can see that better now on the screen.
Yes.
And then this comes out to be
0.2798.
it's roughly 28%. Is 27.9 blah blah blah. But then what you do is you take that and you multiply by 50, because see, there's the difference between these is 50, and then you add it to 500. Okay, I'm going to do that. It's 514. See, it's closer to the 500 because 07 is closer to 068 than it is 73.
Okay, gotcha.
You're okay now, Mohammed?
Yes, I got it.
Yay, good going. All right, well, let me show you one more of these kind, if you're all happy with that. All right, we're going to do another kind. Let me erase these, and remember what we have up here are the values in your table in the back of the book. They've been compared to actual physical temperatures and pressures and volumes in the real world for steam in this case. But here's the kind of thing you might run into. You might run into a problem that you have water. It's at 500 degrees Celsius. But the pressure is something weird, like maybe 5,280 kilopascals. Well, see, that's not in the table. We've got 5,000 kilopascals, and we've got 6,000, but we do not have 5,280. So what do? Well, see, what we want 5,280. They don't have it. And we're trying to find this mysterious specific volume it's going to fit in between these two because it's 500. We've got to find what that specific volume is. We know it's going to be between these two numbers, don't we? We don't even need the 550 anymore. Let me just erase that. What we're trying to find is when the pressure is 5,280 kilopascal. We're trying to find that specific volume at 500 with that pressure for water. Well, here's the plan. Find out how far it is from here to here and how far it is from here to here. Okay, and find the percentage there. Let me make some room here and we'll do it. See, from here to here is 280. But from here to here is 1,000. So what's the percent? Well, you know what? It's 28%, isn't it? What we want is 28% of the way from here to here. Now you got to be careful though, because these numbers are getting smaller. So what we're going to do is we're going to take 20% of this difference here. We'll take 28% of that, but you're going to have to subtract it from this first one. So we're going to take and subtract that from the 0.06857. Okay. So here goes. Well, I got an answer. And what my calculator says is if you have water and it's at 500 degrees Celsius and it's at 5,280 kilopascals, then the specific volume is 0.06523. Does that even make sense? Let's put it in here and see if it does. We think what goes in here is 0.06523. Yeah, it kind of makes sense. Yeah, 0.06. I think that's right. Looks good. Did you understand that? Probably not.
Professor, I don't see from what you wrote on the board the 0.28 times the difference. I don't see how you got the answer from that.
Well, let me do that. Let me try it again. Maybe I did it wrong. 0.06857 minus 0.05665. And then you multiply by 28%. And what all of this is equal to is 0.0033376. And you're going to have to subtract it because the numbers are getting smaller. See? So I'm going to subtract that number from the 0.06857. And I get 0.06523. Now, who was I just talking to?
Nathan, and I missed that step there, the subtraction. I got it now. Thank you.
You're okay? Yeah. Thanks for asking. Well, there you have it, and we'll be doing a lot of that. Don't feel bad if you're confused. I don't know what it is, but this confuses a lot of my students, and I mean, even some bright, brilliant students. They just, I don't know what it is about this. They just don't like it, I guess. That's how you do it.
Is this one of those things that there's like 3 or 4 different ways to get to those numbers? Because I'm not seeing the intuitive side of it yet, but
Yeah.
it seems like there's more ways to do it.
Yeah, I could give you the different ways of doing it, but I think this is probably the easiest. What you do is, if you want something in between these two numbers here, if you want something in between those two numbers there, then you want something in between these two numbers here. And if going from here to here is 28% drop, you're not increasing, you're decreasing 28%, then you want to decrease from here to here 28%. I don't know, it kind of makes sense. That's probably the easiest way for me to try to explain it. We'll be doing it a lot more. If you're taking notes, go back over and study these notes. Now let me talk to you about, back to these models again. We talked about interpolation. And you know that the best model is the tables. Now I erased the 550 table. We'll just play with this 500 Celsius table. At 5,000 kilopascals, there's your V. At 6,000 kilopascals, there's your V. And according to the table, if you have water at 5,000 kilopascals, 500 Celsius, your specific volume is 0.6857 cubic meters per kilogram. This is your best model. It's the best model. But now let me show you the ideal gas model. The ideal gas model, the way you go is you go PV equals RT. Now you're not going to get the best answer. Like I told you before, it's not as good. Now the pressure is 5,000. We're going to solve for the V. Now the R you would have to look up. Go to the back and help me find it for water, for steam. They don't have an ideal gas constant for liquid water, but they do have one for steam. And it is on page, table A5. A.5 in the back, steam is 0.4615. But now here's the catch. The temperature's got to be in Kelvin. So you have to add 273.15. So if you take 500 and add 273.15, what do you get? Is 773.15? Did I do that right? I think so. And this will be the specific volume if you use the ideal gas model. Okay, here goes. 0.4615, 773.15 divided by 5,000. I'm getting 0.07136 cubic meters per kilogram. Now let's compare that with the correct answer. Where is the, yeah, here's the correct answer. It's 68 rounds off to 69, 71. Well, you know, that's pretty close. 69 is pretty close to 71, isn't it? That wasn't too bad. But I'll show you another model. I need some room here to show you that. I've shown you about interpolation. Let me just erase all that, and we'll show you the compressibility model.
Dr. Griffin, could you explain the value, that 773.15? I forgot what that was.
Oh, thanks for asking. Now the temperature is, I erased it, didn't I? Dang it. No, there it is.
500.
500 degrees Celsius. Now, if you'll take 500 and add 273.15, now see, that's Celsius. You get Kelvin. Not Kevin. Kelvin.
Excellent.
573.15. There we go. We've got degrees Kelvin. That's where it came from. No, that's wrong. How about 773.15? You okay? Who was that just asked me?
That was Taylor. That's me. And
Taylor,
yes, I'm great.
Okay, he's happy now. All right. And now we're going to do it with what they call compressibility. Okay. And we know we have water. We know the pressure is 5,000 kilopascals. We know the temperature is 500 Celsius. We know that the thing is, if you have a table, you don't need to use compressibility. You don't want to use the ideal gas either because it's not as accurate. But I'm going to show you that the compressibility is better than the ideal gas. Okay, well, here I need this room here to show you. In order to find this, you have to find what they call the reduced pressure, which is your actual pressure over your critical pressure. I haven't explained that to you yet. And the reduced temperature, which is your actual temperature in Kelvin, divided by the critical temperature in Kelvin. Let me get these here. I'll explain what they are later. But right now, you've got to go to a table. Let me dig around here and find it here. Yeah, here we go. This is table A, table A.2. It's in the back of your book there someplace. Now our pressure is 5,000, but see, that's 5 megapascal. And the critical pressure for steam is, let me see if I can find it here. There it is. It's 22.12 megapascals. I know I haven't explained critical pressure, but I will. And now the temperature is, it's got to be in Kelvin though. It's 773.15. And you have to divide by, you go to table A.2 and you find water, and you divide by 647.3. If you know how to go to your tables, some of you might have figured it out. See if you can find table A.2 and find those critical values. If you have an actual steam table, you don't want to go through any of this jazz. This is a kind of a pain.
I think it was, oh, you already have it.
Say that again, please.
I thought you were still looking for the value, but I see you already have it.
Yeah. And we're just going to divide those now. Let me see what we get here. Let's see. 5 divided by 22.12. 0.226. And now we're going to do this one. This is a 773.15 divided by 647.3. I'm getting 1.19. There's no units on these. They're just ratios. They have a fancy name. This is called reduced pressure. It's in your book. You could read all about this stuff. And this little guy here, that's called critical pressure. I'll explain what that is. Or you could, hey, you could read the book. That's a thought. You could read the book, yeah. And see, this is reduced temperature. And this is your actual temperature, and this is your critical temperature. Let me just tell you this, what those critical things are. We're going to discover that things like water and ammonia and the refrigerants, they can change from vapor to a mixture where you have vapor and liquid. And there's a dividing line between where they change from pure vapor to a vapor and a mixture. And that dividing line is where you have your critical temperature and pressure. Maybe that'll help you understand those. Okay, now we got one last step to go, and we're going to find the answer using compressibility. And here's your compressibility equation. Now remember, here was your ideal gas equation. Here's your ideal gas equation. This is called the compressibility equation. That's it. And this little guy right here, that Z thing right there, that is called the compressibility factor. Okay, we're going to find that factor. Here we go. To find that factor, you have to go to a graph diagram on page figure D1. We're going to go to figure D1. It's kind of in the back of your book back there. It's Appendix D. It's in Appendix D, as in Delta. I'll show you what it looks like. It's, I don't know if you can, I don't know if I don't think it shows up very good. But there it is. See,
Which
see
side of
where
the page?
it's
Okay.
it's on page A77, appendix 77. See where my finger is wiggling? There's a diagram back there. And we're going to find out this, what they call compressibility constant or factor. What you have to do is you have to go to 0.226. Well, it's really hard to show you guys on a computer, but we'll do the best we can. Now notice there's 0.01, 0.1, and 1. 0.2 is right here. 0.226 would be right about in here, where I'm, I don't know if you can see that. And what you have to do is you have to come up here to where it says a temperature of 1.19. How about 1.2? Round it off to 1.2. Hey, do you see that 1.2 right there? I'm going to come up here to where it says 1.2. And I'm going to follow that 1.2 over to where I've got the 0.226. And it looks to me like the value for Z is about 0.96. Here, let me draw you. Let me see if I can draw you a picture of that. You've got a 1.2 that does this, kind of like that. There's a 1.2. And down here, you have a 0.226. You come up here. This is 0.226. This is 1.2. You go over here, and the Z is 0.96. That probably didn't make a lick of sense to anybody. Read the book and let's plug it in though, and I'll show you that this works pretty good. I just need a little room here. Here's a little bit of room. There's some room down here. There's a little bit of room right down in here. And what we're going to do is we're going to go PV equals ZRT. Well, the pressure is 5,000. And we're going to solve for V, and the Z is 0.96, according to that diagram. And the R is 0.4615. And the temperature in Kelvin is 773.15. Okay, solve that. Why don't we put a little Z on here so I can remember that's what you get using compressibility. Let me do that and we'll see what we get. Well, I got an answer. And now this answer here was with the ideal gas model. And this answer here was with the tables. Here, let me circle these. That's the answer we got just looking it up in the table. You all understood that. Now, using the ideal gas model, this is the answer we got. But using the compressibility, using this equation here, this is the answer I got. We did this 3 different ways. Of course, the table is the best way. The ideal gas law is a little bit off, but not terrible. But look at the compressibility. It's pretty dang close. Actually, there's a 1 right here, if you round off. Hey, look at that. 0.06851, 0.06857. I think the compressibility gave us a slightly better answer than the ideal gas law. So I've shown you how to use interpolation and the compressibility, ideal gas law. Any questions on any of that?
The pressure we use in the compressibility equation is 5,000, right?
Yes, I used 5,000. I used water at 5,000 kilopascals and 500 degrees Celsius. And using the ideal gas law, I got this answer. Using the tables, I got this answer. Using compressibility, I got that answer. Is there any comment or question on anything?
In the compressibility model for the reduced pressure equation,
Yeah,
which table is that again for the value of P and critical pressure?
it's table A.2.
Okay.
You're going to have to learn how to pull those tables up on your computer there or your phone. Let me see if I can find mine. I like a paper book. It's a lot easier. But I've got a table here, A.2. And this gives me the critical pressure at 500, the critical pressure of water, and it is, got lost here. Wrong table, guys. Sorry to lie to you. It's, let me find the right table. Yeah, here we go. It's table A.2. I did that part right. And when you find water there it is. It's 647.3 Kelvin is the critical temperature, and 22.12 megapascals is the critical pressure for water on table A.2. Did that answer your question?
Yes.
You might have to read your book to understand this.
I'm looking forward to getting my book.
Yeah, that'd be good. Well, I've got 15 minutes left. Let's just talk about the ideal gas law a little bit. That wouldn't hurt us, would it? Let me make some room here. I've tried to show you about interpolation. It's the best model the tables is the best model we have. But to use the tables, you have to interpolate. Right now, we're going to talk about the ideal gas model. Sometimes you don't have a table. And so you're going to have to either use the ideal gas model or the compressibility model or some other model. Now, when you guys studied chemistry, I think you learned the ideal gas equation that goes like this. That should ring a bell with some of you. PV equals nRT. Isn't that how you learned it when you were younger and better looking? In this class here, there are 4 different versions of the ideal gas law. I won't give, well, I'll give you all of them. Here goes. This one here is my favorite. Then there's another one that goes like this. And finally, there's one that goes like this. That's wrong, guys. Correct that. Put a line over that R. Okay, those are the 4 different versions of the ideal gas law. Some of you maybe thought there was just one, but there's 4. And we need to know the names for every term in here. P, big V, little n, R with a bar over it, T, little v, R, little m, and a V bar. 1, 2, 3, 4, 5, 6. There are 9 different variables there. And this one stands for pressure. Now, if you're dealing with the SI units, it's in kilopascal. If you're dealing in English engineering, it would be PSI. This one's volume. It's cubic meters, but in English it would be cubic feet. This is called the number of kilomoles. And it's in units of kilomoles. But in English units, it's pound moles. This is our universal gas constant. It's kilojoules per kilomole per degree Kelvin. But in English, engineering, it's foot-pounds force divided by pound mole Rankine. This is your temperature. It's in Kelvin Rankine. This is called specific volume. It's in cubic meters per kilogram or cubic feet per pound mass. This is your gas constant. It's not the universal gas constant. It's the gas constant for water or air or ammonia or carbon dioxide, whatever you're talking about. It's not universal. It's different for every gas. I think I'm running out of space here. these last two items, forget about it because I can only go that far and then they don't show up on the computer there. Well, we have a few minutes to talk about these. Before I do, though, do you have any question? If not, I'm just going to talk about these different terms in the ideal gas laws. Here's
There
your
was a
chance.
couple of questions in the group chat on this. People are asking about the homework problems that don't have their books yet. Is it possible that we could get those questions posted on the or on the Blackboard page?
Oh, that's a great idea. Yes, it's possible. For Tuesday and Thursday? Both days?
They were asking about question 83E,
Okay.
and I guess the other ones that are going to be due.
Yeah, here, that's a good idea. Now, who am I talking to?
My name's Taylor.
Okay, Taylor. Okay, Taylor. Okay, Taylor. Taylor wants me to post the homework. I can do that on the Blackboard because some of you don't have a book yet. Okay, well, I better write this down or I'll forget. But I can do that. And we're going to do it for Monday and Tuesday and Thursday. Taylor, what do you think? Think that'll work?
Yes, sir.
Okay, I've written it down. It's a foolproof plan. Post the homework on Blackboard for Tuesdays and Thursdays. I've got it right there. Anybody else before I get to talk about those things there?
This may seem silly, but that is a lowercase p for pressure, right?
No, there is no lowercase p. P is a capital big P all the time. Now, who am I talking to?
It's Taylor again.
Taylor, yeah, okay, Taylor. No, there is no lowercase p.
Thank you.
Yeah, anytime. Thanks for asking.
Professor Griffin,
Yeah,
will this video be uploaded to YouTube after you're finished?
this will be loaded up to YouTube, but only when my IT person, who is my 30-year-old daughter, gets home from work and is in the mood. Okay? She told me she'll get it up by this weekend. What is today? Thursday. We'll do the best we can, but I hate to promise you it's going to be muy pronto. We'll do the best we can, and Taylor wants me to post those problems because he doesn't have his book yet, and I can do that. Okay, I got a few minutes left, and I want to tell you about these things here. Now this one here has to do with, it's actually kilomoles. Now you might have learned it as moles. So let's just talk about moles for just a minute. What the heck is a mole? Does this show up on the board here? Mole, yeah. You know what a mole is? It's 6.02 times 10 to the 23rd atoms or molecules, particles, okay? How about particles? That's what a mole. Did they ever teach you that in school? A mole is 60 point.
Yes.
Yeah, it's Avogadro's number, right? Avogadro's number. Now that's a mole. Now, if you want a kilomole, which we just write as KMOL, is how we write it. You know what that would be? Now, let me think. Running out of room here. Let me make some room. A kilomole would be 6.02 times 10 to the 26 particles or atoms or molecules. Does that make sense? And you're supposed to say, yeah, yes, it does, Mr. Griffin.
Yes, it does, Mr. Griffin.
Yes. There we go. There we go. Now that's a kilomole. Now there's also pound moles. Now I don't know if you remember this, but a kilogram is equal to roughly 2.2 pound. 2 pounds. And so now this thing, I don't want to foul this up here. So if you have a kilomole, wouldn't you have to have you'd have to have 2.2, or would you divide? Do you divide? My mind is mush right now. I don't know about you guys. No, a pound is smaller than a kilogram. So here we go. A pound mole, let me make some room here. This stuff can be confusing. A pound mole should be well, it'll be 6.02. No, we're going to kilogram moles, aren't we? So, yeah, 6.02 divided by 2.2 times 10 to the 26 atoms or molecules or whatever. Make it atoms. There we go. Usually we deal with molecules, though, like O2 maybe. Molecules. What's 602 divided by 2.2? There we go. A pound mole is 2.74 times 10 to the 26 molecules. There you go. Now you know what a pound mole is. One last thing, and then we're going to have to say goodbye. It's been fun. In this class, there are pound forces and pound masses. Here, let me write that for you. This is the English engineering system. There's a pound force. It's written like that. What that is a pound force. And then there's a pound mass. These are different, guys. This is a pound mass. There's pound forces and pound masses. Now, there is a relationship between the two. It's in your book. It's on page 9. And it goes like this. On page 9 in your book, 1 pound force is equal to 32.174 pound mass feet per second squared. That's the relationship between the two. Well, it's sad, but our time together has come to an end, and I'm going to sign off and say goodbye, but here's your chance, your last chance to say anything. Anybody want to say anything?
Thanks.
See you later.
Yeah, see you later. It's been fun.
Thank you, Professor.
Oh, we
Have a good
enjoyed it.
day.
Thank you guys. I'm going to say bye-bye. Bye-bye you.